Welcome to this lecture on cardiac output calculations using the FICK method. My name is John Boland. In this lecture, we'll have a look at the basic requirements for using the FICK method, the FICK equation itself, indirect and direct FICK methods, the instruments required to perform the FICK method, and the various worksheets we use to perform the calculations. First, the FICK equation. The FICK determination of cardiac output depends on two things and two things only. First, the amount of oxygen consumed by the lungs. That is, oxygen consumption, or VO2. Remember that term, VO2. When you become accustomed to it, it'll be frequently used. And second, the concentration of oxygen in blood, meaning the blood oxygen content in arterial and also that in venous blood. So that the FICK equation for cardiac output consists of four variables, one of which is cardiac output, and the other three are the ones we need to calculate or measure to evaluate the fourth. And that is VO2 and the blood oxygen content in arterial blood, CaO2, and the blood oxygen content in venous blood. So the formula is cardiac output equals VO2 divided by CaO2 minus CVO2. We use systemic and arterial pulmonary artery blood samples and oxygen consumption. And oxygen is used as the indicator, and it's basically as simple as that. To determine cardiac output by the FICK method, we need to know basic patient characteristics, and these are height, weight, age, and sex. We need to do some standard temperature and pressure calculations. We need to use exhaled gas worksheets. We need to have morphometric charts. We need to work out exhaled gas analysis and blood gas analysis. We required specialized instrumentation. We also require specialized instrumentation and experienced operators and skilled personnel to conduct the whole procedure. There are advantages and disadvantages to every medical technique or clinical procedure. This is no different with the FICK method. The advantages are that it's the established long-serving gold standard for cardiac output. It has good repeatability, it is relatively cheap to perform, you're required to do it once only, it provides data on oxygen consumption and blood saturations, and it can be done without fluoroscopy. The disadvantages include its invasiveness, it requires highly skilled staff, it requires intense and regular calibration and maintenance. Patient compliance is an absolute requirement. Some patients are simply unable to perform. There are limitations with stress testing. It can be tedious and time-consuming and therefore is unpopular. And it can be misleading, for example, if the catheter is misplaced during collection of bloods. These are the FICK instruments, or at least what they used to be in my lab before we stopped using it. On the top left is a volume counter, and in fact it's just an old, at the time it was new, gas meter, extremely accurate volume counter. And the other two are blood gas analyzers, and these two need daily calibration with special gas mixtures. Every morning, the first job I did for about 20 years was calibrate these two instruments using these two special gas bottles. And we need this bag, a plastic bag called a Douglas bag. It used to be made of canvas back when plastic didn't exist. And it's connected to a little breathing tube with a mouthpiece, a sterile mouthpiece, which the patient breathes into from an inlet port in this direction and an outlet port in this direction. So it maintained sterility for one thing, and also containment of the exhaled gases over a fixed period of time, usually 2 to 3 minutes. Not every lab chose to have these facilities, and not every lab had the skilled personnel to perform the FICK calculations. To compensate for this, some operators chose to use the indirect FICK method. This means that instead of directly measuring every single value, some values can be inferred from other factors. For example, the AV difference can be derived from analysis of exhaled respiratory gases instead of collecting blood samples, or O2 consumption can be assumed instead of having to collect a Douglas bag, or even by assuming arterial saturation from a finger cuff. Not recommended, but this is still used as it still simplifies the procedure and makes it available to other operators. So let's have a look at the FICK calculations themselves. Let's have fun with mathematics. Have a look at the FICK equation again. Cardiac output equals VO2 divided by the arteriovenous oxygen content difference. And start remembering this terminology now. Cardiac output equals VO2 divided by the arteriovenous oxygen content difference. That's what that little group of letters and numbers means. The FICK calculation involves a two-step process. First, we have to collect lung gases from which to calculate the VO2. And as you saw from the previous slide, the VO2 can be derived by assuming it according to patient height, weight, age, and sex, and applying the indirect FICK method, or calculated directly from basic principles. And that is called the direct FICK. And this is the difficult technique that many labs choose to avoid by circumstance or necessity. And the second step in the FICK calculation process is calculate the arteriovenous oxygen content difference from blood. And to do this, we must first obtain arterial and venous blood. And let's now follow the sequence. First step is collect blood samples. This slide shows blood samples collected from what's called a run of samples, where we take blood samples starting from the SVC and the IVC to the high RA, the mid RA, low RA, right ventricle, one site or one side of the pulmonary artery, the other side of the pulmonary artery, and the left ventricle. We only need to take one arterial site because all arterial blood samples with a left ventricle, aorta, or a peripheral artery will have the same saturation. In this case, we took a left ventricular sample. What we do is we then measure the oxygen saturation directly and then calculate the oxygen content. First, I want to point out that all we need for the FICK method is the pulmonary artery sample and the left ventricular sample. The pulmonary artery sample represents a truly mixed venous blood sample. It's the point at which all the different venous bloods from different sites of the body, the brain, the liver, the limbs, are well and truly mixed enough together to be representative of a mixed venous sample. Because of streamlining of flow, there can be slight differences, for example, between the SVC and the IVC. There's more than 1% difference. And you can see the range in venous saturations, even within the heart chambers themselves, ranges reasonably widely, for our purposes anyway, from 60, the lowest here is 66.7 to the highest, 69.5. The truly representative average of all those is in the pulmonary artery, which is 66.7, and the truly representative arterial sample is any artery. In this case, it's the LV. Let's go up here to see how we use these values to calculate oxygen content. We take blood and put it through a blood analyzer, and we get a hemoglobin value expressed in gram percent. That means that in this case, 11.1 grams of hemoglobin are present in every 100 mils of blood. We analyze the oxyhemoglobin portion of hemoglobin, and we need to know the maximum oxygen carrying capacity of blood, which is this value. To do that, we take that oxyhemoglobin value of 11.1 and multiply it by 1.36 to give us 15.1. So our oxygen carrying capacity of whole blood is 15.1 in units mil per 100 mil. So there is 15.1 mils of oxygen in every 100 mils of blood, 15.1%. So it's a relatively simple process. Analyze your blood sample, get your hemoglobin, multiply it by 1.36, and get your oxygen carrying capacity, which is your maximum theoretical carrying capacity of blood for oxygen. Now, if we take our blood saturations and multiply that oxygen carrying capacity, 15.1, by that percent saturation expressed as a fraction, so the 69.5 becomes 0.695 times 15.1, and that becomes 10.5. You do that 15.1 times 0.682, we get 10.3. 0.679 times 15.1 becomes 10.3. If we go down the track, we get 0.667 multiplied by 15.1 gives us 10.1, and finally 0.965 multiplied by 15.1 gives us 14.6%. We now have two of the values needed for our calculation, our arterial and our venous oxygen content. The difference between these two will give us our arteriovenous oxygen content difference. So basically, we need only two blood samples, any arterial and a truly mixed venous sample, which has to come from the PA, the pulmonary artery. And that's why right heart catheterization is required. To date, there's no other way to calculate a truly mixed venous blood sample. So let's have a look at step one in the whole process. We've seen the blood gas analysis, but the step one, arbitrarily, is lung gas analysis. And we're looking at a different patient this time. So the patient data, the patient is 168 centimeters high, weighs 54, also aged 54, female, heart rate 76, and has a body surface area of 1.6. Now we can obtain her VO2 by two means. We can assume it according to the expected value from height, weight, age, and sex from morphometric charts, or calculate it directly. And that is the difference between the direct and indirect FICK method. To do it directly is an involved technique. We need to have that Douglas bag, and we need to have the patient breathe into that bag for 2 to 3 minutes, and then we need to correct that exhale gas, which is saturated with water vapor from the lungs. We need to convert it to standard temperature and pressure. So that, for example, in this patient, we collected 8.3 liters. we have to multiply it by this correction factor for water vapor pressure and obtain 7.4 liters at standard temperature and pressure. We also need to do a gas analysis. We need to measure oxygen content and carbon dioxide content, and that has to also agree with the nitrogen content, which, allowing for a little bit of error, is around 80%. So in this patient, we measured the oxygen to be 18.4% and the carbon dioxide content to be 1.6%. And that 80% is the difference from 100% after we subtract these two. And that is a representation of our error margin. Now, the next step is to calculate the oxygen percent difference. And we use a formula, and that is the nitrogen value, the nitrogen percent, times 0.265 minus the oxygen percent. And in this case, that gave us 2.8%. So that VO2 then becomes volume expired at STP times the O2 percent difference times 10 becomes 7.4 liters times 2.8% times 10, which gives us 207 mils per minute, which is where we got that figure above. So we have a choice at any stage to assume the value, which our morphometric charts tells us is 200, or calculate it by a rather tedious methodology to obtain a value of 2.7. We're often fortunate enough to find they're very close, but frequently they're mismatched, and that's understandable because the patient may be in a different state of anxiety or a different state of health or for any other number of reasons. So to quickly recap, the Douglas bag collects gases contaminated with water. So we have to compensate, and we can do that by using a simple, well, not so simple, but by using a chart that gives us a value to compensate for that. So we have that patient's volume through our volume counter. We simply multiply that by this factor to get that value, 7.4. We can actually measure a percentage of oxygen and carbon dioxide in that gas bag and obtain the residual value to give us a realistic equivalent of what we know nitrogen should be. And we use this formula, which tells us the O2% difference is the nitrogen, 80, times 0.265 minus the oxygen, 18.4. And that gives us 2.8. And the VO2 is that volume exhaled at standard temperature and pressure times the oxygen percent difference times 10. That is simply these two figures, 7.4 times 2.8. Volume exhaled or expired at standard temperature and pressure is 7.4. The O2% difference is 2.8. And we have a unit compensation factor of 10 to give us our final value. That intrinsically is not a complicated equation, but it is confusing, and I can understand that. And we will work through some examples to try and clear it all up. Step 2 in this patient is to do the blood analysis. But remember, you don't have to do it in this sequence. You can do your blood first or your gas first. You can do them together if you have more than one operator. It just depends on circumstances on the day. We can do our arterial saturation, and in this patient it was 94.8%. You'd expect it for a normal patient to be about 95 to 98%. Your mixed venous saturation, your pulmonary artery, in his case, was 69%. His hemoglobin was 12.2 gram percent. I tend to use units, but for simplicity, I'll try to avoid using them and just use the whole numbers for these examples. The oxygen carrying capacity is 16.6. And remember, we obtained that by taking the hemoglobin, 12.2, and multiplying it by 1.36 to give us 16.6. Everything's straightforward. Now, the arterial oxygen content, we take that percentage, express it as a fraction, 0.948 times 16.6 to give us 15.7. Similarly, for the pulmonary artery blood, we take 69, express it as a fraction, 0.69, multiplied by the oxygen carrying capacity, 16.6, to give us 11.5. And we have our blood values that we need to calculate our arteriovenous oxygen content difference, which is 15.7 minus 11.5. So in this patient, our FICK cardiac output is VO2 divided by the arteriovenous oxygen content difference, which is 207 from the previous slide divided by 15.7 minus 11.5. 207 divided by 4.2, which gives us 4.9 liters per minute. It's again as simple as that, provided you understand the steps. That's the important thing. Any dummy can punch a calculator to get a value. But to be a cath lab tech, at some stage, you no doubt will need to know how to do a FICK cardiac output. Though no doubt, but not too long in the future, they'll find some other clever way that will avoid all this. In fact, there are some technologies now, metabolic hoods, for example, but not many hospitals have them. To do a worksheet requires 4 sets of collections of data. And I've used the same worksheet for 20 years and longer until we stopped doing it. We need our patient details, height, weight, age, and sex. We need to do a lung gas analysis. Well, we need to work out, well, first collect the exhaled gases over a period of 2 to 3 minutes. Then correct for standard temperature and pressure by excluding the effects of water vapor from the patient's gases, and then perform our calculations to work out our VO2. Or, and I'll show you that as well, how to assume the value according to the patient's height, weight, and sex. Then we do our blood gas analysis, where we calculate our saturations, work out our oxygen contents, and apply both together to work out our FICK calculation. Systematically done, it's straightforward and you get into the habit.